All right, also, like I said, the first 2 minutes here, I'm going to talk to you about the conditions that favor a positive entropy change. And so that means moving from more ordered to more disordered. And don't forget, the universe favors disorder. So we have, I think it's 5 things that we are going to list out as situations that favor a positive delta S. First one is when a compound goes from being a solid to a liquid. And the second one is when a compound goes from being a liquid into a gas. And of course, in both those situations, I think you understand that you're going to have not only the increase in kinetic energy, which will lead to the particles becoming more further away from each other, but they're also going to be more scattered, which very much connects to the next one, which is when you add heat to some sort of compound or situation. And again, if you're increasing the kinetic energy, you're going to be making those molecules move potentially further away from each other and certainly in a less ordered situation. Next one is dissolving solids in water. And actually, it doesn't necessarily have to be water. I suppose it could be any solvent. But we have a situation where you start off with a compound, let's say sodium chloride, NaCl. You dissolve it in water so it breaks up into its ionic components. And then lastly, the one that is actually connected to what we did in the test that I didn't prepare you very well for, which is when reactions increase the number of particles from the reactants to the products. And so if you look specifically at what I showed you on the test, in this case, you can see here that we take 2 particles, combine them into 1 particle of CO2 gas, and so that is the opposite of increasing entropy. In fact, that's making something more ordered. Okay? Now, I know that you may look at this and think, oh, wait, but it's going from a situation where we have a solid going into a gas. That is the case if there was nothing else going on. But in this situation, and also keep in mind that's a single compound. So if I had dry ice or carbon dioxide that was solid going into carbon dioxide that was gas, then indeed that would be a positive entropy change. Okay, let's move on to what I want to talk about today. Okay, so let's take a look back at what we did in class today, where I talked about or had you guys do some discovery about intermolecular forces. And clearly, we all know that we have this thing called dispersion forces, another one called dipole-dipole, and the last one, which are the hydrogen bonds. And notice that I've arranged them along the spectrum from the weakest to the strongest, except that I spelled strong stronger. That was nice. And I should write strongest. And this has a lot to do with the permanence of the dipole that exists. Don't forget that with the dispersion force here, the dipole that exists is very temporary. With the dipole-dipole, it's a permanent, and with hydrogen, it's also permanent. And the strength difference between these two has a lot to do with the difference in electronegativity that exists among the atoms that make up the compound that we're looking at. And that's going to be a really vital part of the next concept that we're going to be talking about, which is boiling point. All of us are familiar with the concept of what happens when you put a pot of water on the stove. As long as we put in enough energy into that water, then the forces that hold that water as a liquid water are going to be overcome, and it's going to turn the water into water vapor and eventually lead to boiling. And we also know that the temperature at which that takes place is going to be at where we are at sea level is going to be 100 degrees C. So the boiling point is the point at which the liquid turns into a gas or goes into a vapor state. You should also know that we can refer to this as in the opposite direction as the condensation point here. So when a vapor moves into a liquid state, that's going to be the condensation point. And again, in this case, it's going to be at 100 degrees Celsius if you're at sea level. And we're going to assume that's sort of 1 atmosphere. So what is actually happening when something reaches its boiling point? Well, this is where we go back to this stuff. No, not this stuff. This stuff, the intermolecular forces. Because that boiling point is when the intermolecular bonds that exist between or among all the particles that exist are overcome by the kinetic energy that you added to the system. So let me just draw a little bit of a picture here to help you understand that. Imagine we have a couple of molecules here and they have relatively low kinetic energy, so they're maybe vibrating in place here, and they're close enough to one another such that this bond exists between them because of the dipole situation that you can see here where the positive and negative attract one another. Now, if I were to add heat, it would cause these guys to move a little bit more, right? And it could be that they don't even just move in place, but they actually start to move or want to move away from each other because they gain so much kinetic energy. That point where those dotted lines there are snapped, where they break off, is when it's gained enough kinetic energy, those two molecules have gained enough kinetic energy to be able to overcome that bond. So that bond then disappears and these dudes are able to say, see ya, I'm out of here, and go in opposite directions. And if that's the case and they really separate far away from one another, then we know that the molecules have gone into their vapor state. Now, I did just say a moment ago that we know that the temperature of 100 degrees C is the boiling point for water. And that was at 1 atmosphere of pressure. Now, you might ask yourself, what does pressure have to do with this? Well, it has a heck of a lot to do with this because don't forget that this idea of going into a vapor state means that the gas phase is able to evolve away from the surface of the liquid. Now, think of this sort of like imagine that the water molecule has just moments ago gained enough kinetic energy to peel away from its pals that are in a liquid state and go into a gas form. And just above that beaker, there were a whole bunch of guys with mallets that are slamming down on top of that water molecule as it goes into that vapor state. Now, if one of those mallets happens to coincide or hit that water molecule as it goes up, it's going to bounce right back down into the water, and as a result, it might fall into the water, lose a little of its kinetic energy, and go back into its liquid state. So the more of those so-called mallets that you have pounding on the water molecules as they immediately start to lift off the surface of the water, the harder it's going to be for them to stay in that gas phase, into that vapor phase. So I want you to imagine this situation. Here I have a sort of side view of Death Valley and Mount Everest, and I have right along here, this is our sea level. So you can see that Death Valley is quite a bit below sea level. In fact, why don't I draw sea level as this dotted line going across here? Whereas Mount Everest is quite a bit above sea level in this situation. So if I were to be hanging out down here, let's say that I'm the green asterisk down here, and I'm trying to boil water down here in Death Valley. I have a huge column of air that's for all the thickness of the atmosphere above my head or above the pot of water. So that means there's a lot of pressure pushing down on any vapor that might go into a vapor state, and it would get knocked right back down into the vessel of water. Similarly, if I'm hanging out here at the top of Mount Everest and I'm trying to boil water, the atmosphere, there's a much smaller column of air above that water. And so it's going to be a lot less pressure, and therefore it'll be easier for you to have a vapor go into, a liquid go into its vapor state at the top of Mount Everest. It would take a lot less kinetic energy, in fact, to make water boil at the top of Mount Everest as compared to the amount of kinetic energy it would take to boil water in Death Valley. What that means is the boiling points are going to be different here. So the boiling point, say, down at the base of Death Valley is going to necessarily have to be a higher boiling point. You're going to need much more kinetic energy, and therefore the temperature associated with the boiling water at Death Valley is going to be higher than 100 degrees C. Just the opposite is going to be the case at Mount Everest. You can boil water at a lower temperature than 100 degrees C at the top of Mount Everest because the boiling point is lower when you have lower atmospheric pressure. All right, so I want us to return to this concept for a moment of the water boiling in a container. And we're going to talk about something called equilibrium vapor pressure. Now, this is actually a pretty simple concept, but for some reason students, they get all verklempt about this because it sounds scary when it's really not. But I want you to imagine I'm boiling water. And so the water is turning into vapor above the liquid. So this is the liquid phase, and this is the gas phase that we have going on here. And as it's boiling up, for the most part, you can imagine these gas particles are just going up and out, and they're unimpeded. Now, of course, I just got through talking about how the atmospheric pressure does have some impact, so they're not totally free to roam, but you can imagine if I have an open-topped container, the vapor is just going up and out. So if I were to measure, say, the pressure in this area right here in an open-topped container, it really would not be that different from atmospheric pressure. I think you would understand that because the atmosphere is pretty big. The particles of gas, relatively speaking, are pretty small relative to the number of particles of gases that are out there already to begin with. So it's not going to change the pressure appreciably. However, imagine instead of having an open-topped container, I were to seal this container and close it off so that if anything boiled off, it would actually get stuck inside this small space right here above the water and below the cap, the sealed cap that I put in there. Now, if I go to boil water and it starts to build up in there, the number of particles in this area, in this fixed volume essentially, is going to increase. And when we increase the number of particles in a fixed volume, we increase the pressure. We understand that, right? Now, if there's a way that I could increase the number of particles, I could also increase the vapor pressure associated with this, right? And at a certain temperature, you could imagine if I were to zoom in here and take a look at what's going on right here. So let's zoom in right here on this surface. I got my water action going on here. At a certain point, we're going to have just as many particles because of the pressure that's built up going into the liquid state from the gas phase as we would having the number of liquid go into the gas phase. So this would be an equal situation or an equilibrium. And we would call that equilibrium vapor pressure. All right. Now, keep in mind that equilibrium vapor pressure is not going to be fixed because let's say instead of having this tiny little flame that I have here, so I have this logs and everything, and all of a sudden I decide to make it much bigger. Now I've heated this thing up tremendously, and there are going to be more particles in here. So for this particular amount of energy that I've put in to this system, I'm now going to increase my equilibrium vapor pressure tremendously as a result of increasing the overall temperature or the kinetic energy of the liquid. Got it? So that's what's called equilibrium vapor pressure. And most importantly, equilibrium vapor pressure is going to change with increase in temperature. As you increase temperature, you increase the equilibrium vapor pressure too. All right, and the last concept I'm going to talk about is actually the easiest concept, and it is actually the concept that we're going to use for the some of the word problems that we'll be doing tomorrow, as well as in lab on Thursday, and that is heat of vaporization. So, what exactly is heat of vaporization? It's the amount of heat, and it happens to be in kilojoules, needed to vaporize, which means boil or evaporate, a liquid. And in the case of something that's very familiar to you folks, let's say we take water, the molar heat of vaporization, and that's a very important thing because we always deal with moles here, so the molar heat of vaporization, HOV, is 40.7 kilojoules per mole. So that's the amount of energy. If I had a mole of water, it would take 40.7 kilojoules to vaporize that full mole of water. In this case, so that's about 18.01 grams of water. Okay? Oh, and also you should know here, this is assuming that we're at 1 atmosphere. That's going to be a very important part as we just got over talking about. Okay? Now, well, actually I'm not going to go into that. I was going to talk about sort of the concept of phase changes, but I'm going to hold off on that until our lab or maybe even tomorrow's screencast. So let's look at the kind of question that I could ask here. So here's the question. Imagine that the heat of vaporization, or not imagine, I'm going to tell you that the heat of vaporization for mercury is 59.4 kilojoules per mole. And of course, that's the molar heat of vaporization there. And then the question is, if I have 23 grams of mercury, how much heat do I need to vaporize the mercury? And of course, I want to vaporize this stuff completely, not just a little bit of it. So whenever you see these problems, I know you all know that you need to go through moles to get there. And if that's the case, and I know I have 23 grams of mercury, and I know that 1 mole of mercury is equivalent to, and I would just look this up in the periodic table, 200.59 grams of mercury. That would equal 0.11 moles. And of course, I can use the other equivalency that I just gave you in the problem, which is by taking the 0.11 moles of mercury, set this to the 59.4, which you can see is hanging out right there, 59.4 kilojoules. Oops, didn't mean to put on that last piece. Undo. Per 1 mole of Hg. And when I crank that out, I get the answer 6.8 kilojoules. So it would take 6.8 kilojoules of energy to vaporize all 23 grams of mercury. Aren't those ridiculously easy questions? I hope they are. All right. So tomorrow we will do some, we're going to have a problem set for you guys to sort out that not only does these ridiculously easy questions, but also we'll make sure that you understand the other concepts that we've talked about in this screencast, including equilibrium vapor pressure and also the concept of boiling point. But not this stuff. Boiling point. There we go. Where is it? There we go. Boom. All right. See you guys tomorrow. Bye.